So this next problem kind of builds on our previous sample problem here, kind of in thinking about quantum numbers for an energy level, but just kind of has a laundry list of examples to kind of run through to practice this. So again, just to kind of summarize here, when you're talking about your n values, contextualizing and giving you kind of some real world, what does this mean? This really means, again, the row that you are in the periodic table. And so that'll have more context in our next chapter when we talk about filling these electrons. L really refers to the shape of the orbital. And L values run from 0 to n minus 1. Okay, so it's going to help us kind of figure out what possible values we have here. When you're writing the sublevel name, that really just means writing the n number that you have and then the letter that corresponds to the L value that you have. And again, we'll see how this all fits in as we run through these examples. Possible m sub L values, remember m sub L values run from minus L to positive L, and it's going to be all integers, including 0. And then the number of orbitals really is counting the number of m sub L numbers you have. So see if this makes sense as we kind of run through our first example. So they give us an n equals 3, so on the third row of the periodic table, and L is equal to 2. Remember, for our L values, so L equals 0 means you're an s orbital, L equals 1 is a p orbital, L equals 2 is a d orbital, and L equals 3 is an f orbital. So when we write the sublevel name, you just write down the number that's given for the principal quantum number, and then you convert the L value as a number into the code that it is. So again, this L equals 2 is going to be D. So we'd call a principal quantum number of 3 an L value of 2, so that would be a 3D orbital. Possible m sub L values range from minus L to plus L, including 0, so all integer values. And if we count the number of numbers we have here, that means there's 5 possible orbitals. It doesn't ask us to do this. That means there's 10 possible electrons that could go in the 3D orbital. Going through here, n equals 2, the second row of the periodic table. If L equals 1, that corresponds to an s orbital, so this is 2s. Possible m sub L values, again, ranging from 0 to 0, including all integers, is just one thing, that's 0. So that's 1 orbital. So that means the 2s orbitals can hold 2 electrons. And I shouldn't even say orbitals, it's singular. There's only one 2s orbital. When we're at the fifth row of the periodic table and we're talking about p orbitals, so the 5 p orbitals, m sub L values run from minus 1, 0, and plus 1. So that means there are 3 of those 5p orbitals, meaning we can hold 6 electrons total in the 5p orbitals. Fourth row of the periodic table, now we're talking about f orbitals. The possible values are minus 3, minus 2, minus 1, 0, plus 1, plus 2, and plus 3. That's 7 possible numbers, which correspond to the 7 orbitals, which can hold 14 electrons. So the 4f orbitals, and there are 7 of them, can hold 14 electrons in the periodic table.